Given a transfer function, how to represent a system in controllable canonical form. This is what we will see in this video. Let me take an example transfer function where y is the output and u is the input of the system, and numerator polynomial order here is 2 and denominator polynomial order is 3, where 2 is less than 3. First step is split this transfer function into two parts, where I can write this as y of s over x1 of s times x1 of s over u of s. So similarly, in the right side of the equation, I can write this as over 1 times, we have 1 over. Now we are going to associate this numerator polynomial with y of s over x1 of s and associate the denominator polynomial term here with x1 of s by u of s. So the first thing to do is rewrite this expression where y of s by x1 of s is related to numerator. Y is equal to s squared plus 6s plus 8 times x1. And the second expression where x1 of s by u of s is given by this expression. U of s can be written as s cubed plus 9s squared plus 23s plus 15 times x1. Now let us solve this equation first and then we will go to the u of s equation later. So let me rewrite this. Y can be written as s squared times x1 plus 6s times x1 plus 8x1. Now I'm going to rewrite this into time domain form where y is equal to s squared times x1 is x1 double derivative. So we can say x1 double dot is actually double derivative of x1 in time domain. So we have x1 double dot here plus 6 times x1 dot. As we are multiplying x1 with s in s domain, in time domain it would be x1 dot is equal to 1 time derivation of x1 and then plus 8 times x1. We're going to define that x1 dot is equal to x2. We're defining a new variable called x2, which we are saying is equal to x1 dot, and we're defining another variable where x2 dot, the derivative of x2, is equal to x3, which is nothing but x1 double dot. Now how many such variables should we define? Like here x1, x2, x3. Can we define x4? Of course not. We conclude this based on the order of the transfer function. The order of the transfer function is nothing but the order of numerator or denominator, which one is the highest. So we have here 3, which means we should be using only 3 state variables. So we are defining only x1, x2 and x3, not x4. So let me write this output y expression in terms of x1, x2, x3. So we know x1 double dot is x3. So y is x3 plus 6 x1 dot is x2. So we have 6 x2 plus 8 x1. So this is our expression for y, and other important equations are x1 dot is x2 and x2 dot is x3. These are the 3 important expressions we have here. Now let's move on to the second case where the expression is u of s relating to x1. Let me rewrite this again. U of s is equal to s cubed x1 plus 9s square x1 plus 23s x1 plus 15 x1. Now having defined here what is x1, x2, x3 and relation to x1 dot, x2 dot, so we can rewrite this expression as, we know 15 x1 is simply 15 x1. Now I need to convert this into time domain, so u is equal to, now this x1 is a small variable representing it is in time domain, plus 23, we can say in time domain this is x1 dot plus 9 x1 double dot plus, here we have x1 triple dot because 3 times derivative in time domain. Now we can rewrite this expression as 9 times x3 because we know x1 double dot we defined here as x3 plus 23 x2 plus 15 x1. Now we have here x1 triple dot. We don't have to define the x4 variable because the order of the system is 3. So we need to write this as x3 dot. So this becomes our final expression. Now using all these 4 equations, we'll represent them in standard matrix form. We have derived all these 4 equations from the previous slide. So let me rewrite this fourth equation, which is in terms of u and state variables, into x3 dot can be written as equal to minus 15x1 minus 23x2 minus 9x3 plus u, the input. So now these are the final 4 equations that we will use to represent them in standard forms. So we can say x1 dot, x2 dot, x3 dot is the vector that we are trying to represent in terms of matrix A, which is 3 cross 3, because we know the order of the system is 3. Then the first matrix that we have, A, will be 3 cross 3. We need to find the values of this matrix based on these 4 equations, times we have a vector in terms of state variables x1, x2, x3, plus another vector in terms of u, the input. So in this case, x1 dot we know is equal to x2, which means it doesn't depend on x1, x3, or even u, which means in terms of x1 with respect to x1 dot with respect to x1 is 0, and as x1 dot is equal to x2, we have 1, and it doesn't depend on x3, so 0, and x1 dot doesn't depend on u as well, so 0. Now let's write for x2 dot. x2 dot is equal to x3, which means doesn't depend on x1, doesn't depend on x2, and it is equal to x3, so we have 1 here, and it doesn't depend on u as well, so 0. Now x3 dot, whereas it depends on x1, x2, x3 and u. So let me put the values here. x3 dot is equal to minus 15 times x1 minus 23 times x2 minus 9 times x3, and in terms of u it is 1. So we have the first equation, which is called the state equation, represented with the matrix A, and this matrix we call B. Now let's find the output equation, which we write y is equal to, in terms of state variables x1, x2, x3, plus if it depends on u, we need to find the value of the coefficient. This matrix we call it as C, and this matrix D. Here this matrix is actually a single value, so we can say a small d. Now let us find y in terms of x1, x2, x3 and u. We already have the expression. We can say y is depending on x1 with 8 value, so 8. In terms of x2 it is 6, and x3 it is 1, and output directly doesn't depend on input, so there is no u in this expression of y, so this is 0. Now for controllable canonical form, you have the standard way of representing. You will have this once just above the diagonal of the matrix once, and you have this one of the row to have all the values. Now let's see how the signal flow graph looks based on these equations. If we know x1, I'm taking x1 as a node, and x1 to x2 there is a dependency where x1 dot is x2, which means I can write here x1 dot, which is also x2. So if I integrate x1 dot, we will get x1, which means 1 over s is the integrator transfer function. So I can say x1 is equal to integration of x1 dot, which is nothing but x2 here. x1 dot is x2, we have seen here, and we have another one which we will call x3. x3 is nothing but x2 dot. So if I integrate x2 dot, I'll get x2 here, 1 over s, integrator. If the signal goes from here, it gets integrated and we get x2. Now we have x3 dot. If we integrate x3 dot, we get x3. So we have 3 integrators. The number of integrators we have will represent the order of the system. So this is a third order system, and we'll have three integrators. This is x3 dot. We know that x3 dot is given by minus 15x1. So x1 is here. I need to take a signal back here and add it. This will be minus 15, and it depends on x2 with minus 23. x2 is here. This signal should come, and this is minus 23. And x3 also it depends. So x3 is minus 9. And it also depends on u, the input. So let's say input is here. Magnitude is 1. So x3 dot from the signal flow graph we can say is u minus 9 times x3 minus 23 times x2 minus 15 times x1. So that's what the equation represents, and you get the same from the signal flow graph. Now let us see how to represent y here. So y is equal to 8 times x1. So I'll take a signal from here, 8 times x1, but not just that, it depends on x2 and x3. So x2 is here, 6 times x2. So I'll add here 6 times x2, and we have 1 times x3. So let me take it here, 1 times x3. So this value is y. So for convenience sake, I'm taking another node saying y, but both are same. So y we can say here 8 times x1 plus 6 times x2 plus 1 times x3. That's what the equation represents here. So this is how the signal flow graph looks if you represent the system given by the transfer function in controllable canonical form.